Get off my side, table, dude. Look, see this? The line, bro. I opened my binder. Look at me. Oh, wait.
Kai, you're being really sensitive. Okay, acceleration. Again, this is an exercise, like so many things in Physics 11, this is going to be an exercise in reframing or tearing down little bits of what you already feel like you may understand, and reframing it all again, new language, new expectations, maybe some new notation. What does it mean to accelerate? How do we use that word in physics that's perhaps different than how you're familiar with using it? So imagine, if you will, that you're sitting at a stoplight and suddenly the driver hits the gas. What do you feel? And again, depending on the vehicles that you've sat in, your experience of this is going to change. But imagine you are sitting at a stoplight, the driver slams on the gas. What does that experience feel like to you? Brad.
Your body getting like pulled into the seat.
Okay. Body gets pulled into the seat. Emma, I thought I heard your voice underneath Brad's voice for a second. Like a pull? Same kind of thing? Like. You don't know how to explain it? Anybody else would explain it differently than perhaps Brad has? Yeah, Henry. Ooh, G-forces. What the heck is a G-force? Okay. How else would you describe that experience? Would anyone describe it differently than how it's been described already? Okay. So what I'm hearing you all of you would agree that it feels like someone grabs you and pulls you back into the seat. Okay. Henry, what's a G-force? You just know it's a thing?
I know it's
Okay. Affects your, how did you say it? I'll come back to what you just said, Lachlan, in a second. Henry, you said it affects your what? Okay. Lachlan, what did you just say? That's not what you said. That's what Henry said. What did you say? No, but I liked what you said.
What did I say?
I don't know. What did you say? You're talking about it being a multiplier.
Oh, yeah, gravity multiplied onto your weight. I don't know. I can't know what I said.
Okay. It's gone. Yeah, I know how that goes. G-forces, I mean, not something we often talk about as it relates to driving in a car, but it's a thing. G-forces often get discussed more aggressively when you're talking about things like an astronaut at a rocket launch or in an aircraft, because those are a little more dramatic. I guess it depends on the kinds of cars you've sat in. And how you, again, the cars you sit in are really going to impact your experience of what it looks like to slam on the gas. If I put you in my car, my first car, my 92 Civic hatchback, and you're sitting in the front seat and I slam on the gas, you're not going to feel much. It just kind of slowly drags you forward. But even then, you kind of hardly notice it because it's a 92 Civic hatchback. The first time I ever really experienced this, my cousin was obsessed with Skylines back in the day. There's lots of people who were. It was the early 2000s. Skylines were a big deal. The right-hand drive here in Canada was a novelty, and so people spend their money on it. Or later on, I had a buddy who was like one of the first adopters of Tesla that I'd ever met. He was an early investor, sold out his stocks and bought like the first Tesla. And then he took us all for a ride. You sit in the front seat of that thing, and it was late at night, and he slams on the gas, and it really was that feeling of getting sucked into your seat. Imagine you're driving now at 50 kilometers per hour. Let's look conservatively, 50 kilometers per hour, and the driver, whoever it is, maybe it's you. Often, if it's you, You brace yourself subconsciously. So you're the passenger, and the driver slams on the brakes. What does it feel like to you at that point? You're not paying attention. You're on your phone. Driver slams on the brakes. What is that experience like, Brad?
Getting pulled the other way, so instead of being pulled into your seat, I get pushed forward.
Okay. Do you want to share that with the rest of the class, Walker? Do you want to share that with the rest of the class? You don't? It was good. You say it once and then it's gone so fast? Gotcha. Okay. You should record yourself. You discuss going over a train track and getting thrown into the air. And you feel that a little bit in your stomach. Yeah, if you go up and down, that's what it feels like. Emma. Say that again. Okay. So there's another way to describe exactly this scenario. In one sense, it feels like you're getting launched forward. But in another totally equivalent sense, another way to describe it is what Emma just said. While it feels like perhaps you're being pushed forward, you could think of it like this. You continue to move as you were, and the car slows down behind you. So perhaps it feels like you're getting pushed forward when in actuality, you're not getting pushed forward anymore. The car is just no longer carrying you forward, and your body just kind of wants to keep going. But then, Emma, you said something about getting pulled back again. Who does the pulling back? The seat, and ideally the seatbelt. This is the purpose behind seatbelts. You get an object because this is what it feels like. But this, what I wrote here in green, is actually what's happening. It's a good description of what's actually going on. You continue to move as you were, and the car slows down behind you, and then something has to catch you. In the perfect world, it's a seatbelt. But if it's not the seatbelt, what's the next thing to catch you? The windshield. And if the windshield depends on how fast you're already moving and how quickly the car is coming to a stop. But if the windshield doesn't catch you, what's the next thing to stop you? The concrete, the car in front of you, the tree, some other object outside the car needs to catch you. And nothing is, well, I mean, there's one more thing before the windshield we could talk about. There are layers of, I mean, and that's why these safety things exist. Not because you are getting pushed forward, but because you were getting pushed forward before, and the thing that's doing the pushing is now slowing down. You keep going. This concept has a name. Before we talk about acceleration, what's the name of the concept that once you're moving, you're going to continue to move? Yeah. Unless, Lachlan? Okay. You betcha. So for those of you, and Lachlan just forgot already, an object in motion stays in motion unless acted on by an outside force, or Kai, the one word for that is inertia. Which we're going to, well, you quoted Newton's law directly. Kai gave us the name for it. We're going to talk about it in more detail next chapter. But this is that idea. And there are things, and this is why. So cars have all sorts of safety things that are designed to be the kind things to catch you. The seatbelt, if not the seatbelt, the airbag. If not the airbag, now you have to deal with the dash and the windshield. Those are a lot less kind. But even those are more kind than the concrete on the other side. And so if that's what's actually happening, Emma's description, really, it feels like you're getting pushed forward, but you're not. You're just no longer getting pushed from behind. What really is you feel like, go back to the first one, you feel like your body's getting pulled into the seat, but what's actually happening there? Going back to what Lachlan said, an object in motion is going to maintain its motion unless it's acted on by something outside of it. It's not what he said, but I paraphrase. So instead of your body getting pulled into the seat, if you're sitting at a red light, what's your body doing? You're sitting still. And so your body wants to continue moving that way or not moving at all. And so when the car starts to accelerate around you, you don't get pulled into the seat. It's like it comes up behind you and gives you a hug and then starts pushing you forward. You're not getting pulled back. You want to stay where you are. And the car says, no, you're coming with. Because if it didn't, you would just, if it accelerated fast enough, it would just accelerate right through you. So it feels like your body's getting pulled into the seat. If we come back and apply Emma's explanation, that's not actually what's happening. A better explanation for it is the seat pushes forward around you. So the pink is what you feel, and I'm not trying to invalidate what you feel. That's absolutely what it feels like, but this is a better explanation for it. The seat pushes forward around you. There is an unfortunate scenario where this happens. Has anyone ever been rear-ended? It's the same idea. You were not moving. Car slams into you from behind, and your car jolts forward. What's the injury commonly associated with getting rear-ended? Whiplash. Whiplash happens because all of you is affected by inertia. Your head, your torso. Your head, your torso, all of you is not moving. Then the car behind you hits you. It pushes the car that you're in forward, which pushes most of you forward, except your head, which was not in motion, wants to remain not in motion. And so it feels like you're getting punched in the head backwards, but really your head was just there. And now your neck has to kind of drag it forward. What is the safety thing designed to prevent whiplash in a car? The headrest. The headrest isn't designed to be comfortable. It's not like, oh, the headrest is there so when I need to rest. No, the headrest is supposed to be kind of always at the back of your head so that the seat pushes you forward together so your head doesn't get left behind and give you whiplash. Someone thought this all through. So the things that you felt here, going back to the pink ones, what you're experiencing is the feeling of acceleration, whether you're getting pulled back, pushed forward. This is what we call acceleration. All of it is acceleration. It doesn't matter which direction you go in. Typically, colloquially in English, the feeling of getting pulled backwards when you were moving forward, we call what? We have a name for that. If I asked you what the opposite of accelerating was, you would probably say, starts with a D. Decelerating. Perhaps you don't actually use this word. But in physics, everything is an acceleration. And now we're just going to start to give accelerations names, signs, positive or negative, to dictate which direction. We're not going to use this word deceleration. Whether you're speeding up or slowing down, all of it's going to be an acceleration, and we're going to give signs to it. There is weirdness that shows up. There's weirdness when the velocity you have and the acceleration that you experience are in opposite directions, which we'll talk about today. Weirdness occurs at that point. You just got to be really deliberate about how you understand that. So acceleration is the push that you feel when your velocity changes. Let's talk about changing velocity. Velocity is a vector, if you recall. Vectors are made of two parts. Because velocity is a vector. And a vector is made up of a magnitude. And it's made up of a direction. You bet. when we accelerate, typically, most commonly, you guys think of accelerating as changing this. And so when you change the magnitude of acceleration, what are you doing? Sorry, when you change the magnitude of the velocity, what are you doing? In more common language. Magnitude is the size of something, yeah? So, sorry? You get faster, or the opposite of faster is slower. So typically when you think of accelerations, this is what students talk about all the time. You speed up, you slow down. You get faster, you get slower. But really at that stage, all you're changing is the magnitude. But because a velocity is a vector and an acceleration occurs whenever any part of velocity changes, there's also this piece here too. What does it mean to change the direction of a velocity? What does it mean to change the direction of a velocity? I get to get up and I get to walk around again. I don't get to do this in very many units, but I get to do this in this one all the time. Okay, so this is the magnitude changing. I'm walking faster, I'm walking slower, magnitude changes. Back the other way. If my magnitude stays the same, and I want to change its direction, what am I going to do? Yes. Who said that? Everyone pointing, okay. I could slow down, or turn around, rather, you said turn around. Turning around is kind of an unintuitive way to think about it, because to turn around, really all I'm doing is slowing down and then speeding up the other way. Turning around is really just a magnitude thing. I could go a different way. So here, Rem, do me a favor. I want you to put your arms straight out. And I'm going to grab it as I walk by. So I'm just going to keep going. My speed hasn't changed. But now, when I ran into Kai's desk, what did she do? She changed my direction. I was going this way, and then I grabbed Yerem's arm, and now I'm going this way. And if Kai's desk wasn't here, I would run into Kale and I'd run into Brad after I let go of Yerem, because I'm not going to tear her shoulder off. But this is another way to change your velocity. The magnitude didn't change at all. I was walking the same rate. Let's go to David. This will be a better one. David, grab my arm. And I'm going to go, and I'm going to go this way. My speed didn't change at all. But my velocity did, because the direction changed. So I must have accelerated to do that. When you turn a corner, what is the direction of the acceleration? Do I do it again? How did I turn the corner? Slow down. How did I turn the corner? That's a lot off. David and Rem. What did you feel when I turned the corner? Do it again. For someone else. You know what, Lachlan? Come back here. Let me scan right there. Okay. I'm going to walk by, and I want, which arm hurts on you? Okay, you face that way, and put out your left arm. Okay, I'm going to walk by, and I'm going to grab your arm. Don't move. Okay, here we go. So, I'm going, and I'm going to keep going, but don't move, Lachlan. Don't move, Lachlan, and now I'm going this way. Lachlan, what did that feel like to you? I was pulling you upwards, but what were you doing to me? Pulling me backwards. So when he pulled me backwards, I made the corner. So when we'll talk about circles later. So when you're changing your direction, you're also accelerating. Lachlan, I was a more dramatic version of what I didn't want to put you to any of your seats. But what I just did with Lachlan is a bigger example of that. I was pulling him forward, but he was pulling me backwards. So really, what does it look like which is the direction for the acceleration when you're changing a corner? It's into the corner. Something's got to pull you or push you into the corner if you're going to make it. So, turning is another version of what it means to accelerate. So let's define it. Acceleration. Acceleration is a vector. The symbol is, I've reused it once already. I'm going to use it again right here. It is exactly what you would expect it to be. Acceleration starts with the letter A. So A is what we use to represent an acceleration. What is the definition of acceleration? Acceleration occurs when velocity changes. And what would it look like for you to have a very, very large acceleration? Give me an example of an acceleration that you would think would be a large one in your experience. A rocket. You're not moving, and now all of a sudden you're moving very quickly. Being shot out of a cannon. You weren't moving, and now you're moving very quickly. So acceleration, but I could eventually move at the same speed as the cannon, right? So, I mean, there's two ways to get to, or the rocket. There's two ways to get to that speed. Either I could do this, and slowly speed up to that. That's not going to be as big of an acceleration as when I am not moving. No, sprinting. Sorry, if you could call that a sprint. Okay? Which one of those was the larger acceleration? Coming back. Which means, but I reached a similar speed. So what was different about the two? No, that's what we're trying to define. What was different in how my velocity changed, even though I reached basically the same velocity in both cases? Sorry? Louder. The amount of time it took for me to do that. So in the first one, it took me a lot longer to reach. In the second one, I was a lot less time to reach. So that plays into our definition here. Acceleration is defined to be how quickly your velocity changes, or to give it a better definition, which I'm going to do right here, a more mathy definition, it is the rate of change of velocity. This is how I would recommend you think about it. It's how quickly your velocity changes, dependent on the amount of time it takes for you to reach whatever velocity you've reached. But this is the formal language we're going to use. The rate of change of velocity. So if acceleration is how quickly your velocity changes, it's going to depend on your changing velocity. Delta we've talked about, the change in, Greek letter, means a final minus an initial. V final minus V initial. And we want to know how quickly that happens. So what we're going to do is we're going to take your changing velocity and we're going to divide it by time. The smaller this time is, the bigger your acceleration is going to be. So your acceleration A is going to equal your change in velocity over the time it takes for you to do that. Or you can write it as Vf minus Vi over T. Now this thing has units. What are the units for velocity in the SI system? Sorry? M divided by S. Velocity is meters per second. And I'm going to divide that by time. The units for time are seconds. So then acceleration is going to be meters per second. But that's kind of a gross way to think about it. So we write it a little bit differently. Instead of having a meter per second, That's the same as having a meter per second times 1 over seconds, which, when you multiply fractions, you multiply numerators, you multiply denominators, m times 1 is just going to be m. What's s times s? S squared. So another way to write the units for acceleration is to say that your acceleration is either in meters per second or meters per second squared. These are the two that get used all the time, and almost interchangeably. Meter per second or meter per second squared. So to think about it kind of simply, what does it mean for an object to accelerate at 2 meters per second squared, or 2 meters per second? What does that actually mean? Kai.
Does that mean that every second 2 is getting to it?
Nope.
Every second going twice as fast.
Warmer. You're not doubling your.
Every second is going squared as fast as you were the second.
No, that's less warm than you were before. You were there. You were almost there. To accelerate at 2 meters per second, it means that, let's go and work it backwards. Every second, your velocity is 2 meters per second more than it was before. So it's not doubling, it's adding. Yeah. Every second, you go 2 meters per second faster. So if you're not moving, when time starts, if you are at rest, your velocity is 0. If you're accelerating at 2 meters per second, after 1 second, how fast are you going then? 2 meters per second. After 2 seconds, how fast are you going now? 4 meters per second. After 3 seconds, how fast are you going now? Not 5, 6. Every second, you add 2 meters per second. That's what it means to accelerate at a particular rate. 2 meters per second squared means every second I go 2 meters per second faster. Acceleration is part of the reason why meters per second is the preferred unit for velocity. Let me show you why we like meters per second for velocity. What would it mean for me to take 2 meters per second squared, and I want to put that thing into, well, what would be the equivalent unit in kilometers and in hours? If acceleration is measured in meters per second squared, what would be the equivalent units if I wanted to use meters and kilometers? Well, instead of meters, I would put, if I want, oh, sorry, I'll let Yuli answer. It would be kilometers per hour squared. But my question was, what would be, if I wanted to change this meters per second squared into an equivalent set of units, but the bigger version, so meters to kilometers and seconds to hours, this thing would be written as a kilometer per hour squared. Let's do that conversion. A 2 meter per second squared acceleration means every second you go 2 meters per second faster. This doesn't sound like a very big acceleration, but let's take a look at what that would mean. Let's convert it using the old school methods, like my full factor label, excuse me, my full factor label method into this. If I wanted to do that, my first fraction would be to do what? I need to change both the meters and seconds into kilometers and into hours. Now I want to use the old school factory label method. I don't want to use the shortcut for reasons you're going to see here in a second. We're going all the way back to the beginning. Let's do, sorry. Okay, yeah, let's put meters on the bottom, kilometers on top. That's a great idea. Let's do that. That's going to get rid of the meters. It's going to put kilometers up top. The relationship between kilometers and meters is 1 kilometer is 1,000 meters. Cool. And now I'm going to have another fraction that's going to do what? We're going to put seconds on the top, and I'm going to put hours on the bottom because at this stage, that's a shortcut we can make. How many seconds are there in an hour? Does anyone remember? There's 60 seconds in a minute and 60 minutes in an hour. 3,600. 60 times 60 is 3,600. So there are 3,600 seconds in 1 hour, but I don't have seconds. I have seconds squared. 2 square seconds means I have 2 seconds being like seconds times seconds in the denominator here. So what I need to do is I need to multiply that by another 3,600 seconds per hour squared. Now I have seconds times seconds in the numerator. I've got seconds times seconds in the denominator. This is going to cancel my meters. This is going to cancel my seconds squared. So what is the number? What does it mean to accelerate at 2 meters per second squared in kilometers per hour squared? I saw some people pull out calculators. What's the math? Did you get a number, Brayna? What's the number? Whoa, Kara, that's too big. 25 million? Did you divide by the 1,000? So what we're multiplying across the top and you're dividing by everything in the bottom. So 25,000 is the number that you're looking for. 920 kilometers per hour squared. So 2 meters per second squared does not sound like a very large acceleration. But if you kept that acceleration up for an hour, you would be moving at 25,920 kilometers per hour at the end of that hour. That is very, very fast. Brenda, did you figure out what went wrong with your calculator? Punch it until you get this value. Make sure you can get that with this. Hello, Brooklyn. So even what seems like a small acceleration, if you do it for long enough, can have massive implications. When you're ready, flip the page. Make sure you can actually do this. So you see why I wasn't just jumping to 3.6? Okay, good? Okay. So the rules for the direction for acceleration are the same as they are for velocity and displacement. Generally speaking, we talk about right, forward, up. Generally speaking, those are all positive things. Left, down, back, west are all generally speaking negative. You can change it as it's convenient, but generally speaking, that's how she goes. So what does it mean to have a negative acceleration? It does not, I should have another word in here. A negative acceleration does not only, is the word I'm going to shove in here, mean that you are slowing down. Sometimes a negative acceleration does mean you're slowing down. Sometimes it doesn't. It depends what else is also going on. I'll show you what I mean here. Let's call for all 4 of these number lines, I'm going to call to the right positive. Let's say I've got an object right here on all 4 of these number lines. We're not actually going to use the number line. It's just a good way to have a reference. I've got an object right there on all 4 number lines. On the first one, my velocity is that way. And my acceleration is also going to be that way. So if I have this, if I've got my accelerations to the right and my velocities to the right, that means my acceleration and my velocity are both what? In sign, using the signs, sign conventions. They're both positive. Acceleration is positive, velocity is positive. So if they're both positive, my velocity is moving to the right, or my object's moving to the right, which is why I have the velocity is to the right, and I'm accelerating in the same direction, what is actually happening here? In common language. Don't even use that word. More common language. Speeding up. If you're moving forward and you're accelerating in the same direction, you're speeding up. And that's what these two things, that's the difference between what's here and here. The V plus means I'm moving forward. That is the definition of having a positive velocity. And the acceleration being positive means I'm gaining velocity. Okay, let's do the next one. My velocity is still this way. But now, what does it mean for my acceleration to be the other way? What are the signs now on A and V? Yuli, was that a question? You bet. What are the signs on A and V? A is negative, because we define to the right to be positive. And Emma, keep going. And V is still positive here. So what does that actually mean? Yuli is right. We're slowing down. Why are we slowing down? Because we're moving forward. And we are decreasing V. Let's carry on the scenario. Let's say that A is still backwards, but that V is also now to the left. What are the signs on A and V? They're both negative in this case. What's happening? Colden. Is it? Raina. When you say still, what do you mean still? Because positive and positive meant moving forward, gaining V, so speeding up. Negative and negative, this means, yeah, let's break it down. You're right, Raina. Your negative V means moving backwards. And there's a couple ways to think about this. If we continue to decrease V from a positive value, so my V is going down. So let's say it was at 4. My V was 4, then it was 3, then it was 2, then it was 1, then it's going to be 0. If we continue to decrease V past 0, now it's -1, -2, -3, -4. Now my V, if I have a negative number with my velocity, just means I'm moving backwards. If my acceleration is also negative, and it stays negative, if my velocity was -3 and now it's -4, and now it's -5, now it's -6, V is still decreasing here, but it's getting larger negative. So V is still decreasing in a sense. It's getting more negative. But if it's getting more negative, and it was already negative, this means you're speeding up again. You're just speeding up the other direction. So this is why a negative acceleration doesn't only mean you're slowing down. In one sense, you are. If your velocity is positive and your acceleration is negative, it's going to drag your velocity back to 0. Just slow down. But if your v is negative and your acceleration is also negative, you're speeding up going the other way. Let's do the only other combination we haven't done yet. V is still going to be backwards, but now my A is the other way. What are the signs on A and V? A is positive. We defined forward to be positive right up here at the top. So if A is forward, A must be positive and V must be negative. So if we break down what this means here, negative V just means moving backwards. Positive A means you're increasing V. But what does it mean to take a negative number and increase it? If a negative number is increasing, what is it going towards? 0. And if a velocity is approaching 0, what's the object actually doing? Someone said it. Say it louder. You're slowing down again. So a negative acceleration does not always mean you're slowing down. And a positive acceleration does not always mean you're speeding up. It also depends on how you're already moving when you begin to accelerate, either positively or negatively. And if you take a look at kind of how this all goes, if this is what's happening here, I was moving forward and I begin to accelerate back. If I allow this to continue the whole way, this line is actually going to become this one here. Eventually, this will translate. And it's kind of a weird way to think about this. If I'm moving, the way that we would think about this, a car is a really bad example of this. Because if I'm going to do this in a car, I'm moving forward and I want to accelerate backwards, but I want the acceleration to keep going backwards. I'm not braking. What do I have to do to make this happen? Braking is not the thing to do, because when you brake, once you reach 0, you will stop. Brakes aren't designed to push you back the other way. So if I wanted to do this in a car, if I wanted to slow myself down and maintain my backwards acceleration, what would I have to do? Sorry? That one. If I'm driving forward and I want to do this, I would have to slam it into reverse and punch the gas. My wheels will immediately, well, you drop your transmission out of the bottom of your car to do this. But if we were able to do this, the wheels will start spinning backwards while I'm still moving forward. It'll slow me down and then they'll catch and I'll start accelerating back. More accurately, or less damaging to your vehicle, if I put a giant jet on the front of the car. And I'm driving forward and I flip that jet off, it's going to start to push back against the forward motion of the car. And as it continues, if that jet keeps going, it'll force the car backwards. What happens if this continues? This is the one that actually is easier to do in a car. It's not overly damaging. Let's go back to Emma's example. You're rolling backwards down a hill. If anyone's ever learned how to drive in a standard car, like I did, this is the thing that's going to happen to you. You let off the gas. As you figure out clutch stuff, now you're sliding backwards. What are you going to do to stop sliding backwards in a standard car? Yes, this. You're not going to brake. You're going to put it in gear and you're going to slam on the gas because you want to go this way. If you do that too aggressively, as you're sliding backwards, the wheels are going to start to spin aggressively. You might get smoked, you might get something on the road, but it's going to start to spin. As they catch, your backwards velocity is going to reach 0. It's going to stop you, but then it's going to start to launch you forward. Hopefully not into the car in front of you. So eventually, this scenario is going to turn into this. if we allow the acceleration to continue. And there are all sorts of ways to do this. So acceleration is more complicated than just saying, oh, I want to accelerate, so I push the gas. I want to decelerate, so I push the brake. Actually, there's all sorts of good reasons to say, I want to accelerate, I want to go forward faster. Sorry, I want to go backwards slower, so you hit the gas instead. Emma's rolling down the hill example is a really good one for this, because you're not going to drop the transmission out. But if you're on the freeway going forward and you want to come to a stop, don't put it in reverse. You will drop the transmission out of the bottom of your car real fast. Comments, questions? Yes, sir. You bet. Comments, questions, concerns? Cool, let's do some math. There are 4 equations that govern acceleration in this unit. They are, these ones. Vf equals Vi plus At, d equals Vit plus 1/2 At squared, Vf squared equals Vi squared plus 2Ad, and d equals Vi plus Vf divided by 2 in brackets times t. I do not expect you to memorize those. You bet. Name on the board. Because they're all right here. There's your formula sheet. Here they are. That guy, that guy, that guy, and that guy. How you choose which one to use will be determined by what we've already lined out before. As you're going through to tackle one of these questions, you're going to write out what you know. What you know and what you're looking for will determine which one of these you choose to use. Now I'm going to give you an example. So, a moped is traveling at 18 kilometers per hour. It accelerates at a constant 1.5 meters per second squared for 6.4 seconds. What is the final velocity in kilometers per hour? So, what do we know? Let's go through the process. Based on what I just read, someone tell me something. Sorry? The initial velocity. The velocity that it's already undergoing is 18 kilometers per hour. What else do we know? Or what are we looking for? What about do we know it or are we looking for it? We're looking for the final velocity. So Vf is our unknown. What do we know? We're given the acceleration. The acceleration is given to us in meters per second squared. It's 1.5 meters per second squared. And what other piece of information do we have? We know the time is 6.4 seconds. So our moped accelerates for 6.5 seconds almost at this rate, and we want to know how fast it's going after that has occurred. So we've written down everything the question gives us. What's our first step going to be at this stage? Or our next step going to be at this stage? There's a problem with what we're given. There's going to have to be a conversion. Why did you notice that? Or what about what we wrote down gives you that idea, Emma? But our initial one's also in kilometers per hour, so that's not a problem. What's the problem? These are the problem, yeah. The acceleration's in meters per second squared and the time's in seconds. So because this is in meters per second squared and this is in seconds, what's the conversion we should make to start? Would it make sense to convert both of these into units with kilometers and hours, or would it make sense to convert this thing into meters per second? Yuli is nodding aggressively. She's right. This, even though we want the final velocity in kilometers per hour, it's mathematically easier to convert this into meters per second and then convert your final answer back into kilometers per hour. Converting from kilometers per hour into meters per second means we're doing what? Something with the number 3.6. Do we multiply or divide to go from kilometers per hour to meters per second? It's on the board at this stage. Yeah, you divide. It's on that front board over there. We're going to divide by 3.6. So what is 18 divided by 3.6? You betcha. And now we can go ahead and we can apply one of these kinematic equations. Which kinematic equation? Which equation, there's 4 of them, which of them uses the information that we're given to give us the piece of information we don't have? Yes, the first one. Rushan, you good? Yes, Jaden, were you able to answer his question? Okay. So it's the first one. Why is it the first one? Well, if you look what we have here, we have VI, we have A, we have T, and we're looking for VF. This equation does not have a VF. This one doesn't have a T, and this one doesn't have A. So I can't use any of these last 3 equations. I have to use the first one. So write down the equation. VF equals VI plus AT, and now we're going to fill it in. VF is our unknown, so we're going to leave it there as the variable. VI is 5, because we converted it. The acceleration is 1.5. The time is 6.4. So I just replaced VI with 5, A with 1.5, T with 6.4, and now we're just going to do the math. BEDMAS says we multiply these 2 first, and then we add 5. So what is VF given an initial velocity of 5, an acceleration of 1.5, and a time of 6.4? I'm seeing some calculators. You all should have calculators up. It would make your life easier. All of you should practice with this stuff. What is the final velocity in meters per second? 14.6, you betcha. But I want that number doesn't necessarily mean anything to you guys, because you're not used to looking at velocities in meters per second. You're used to looking at velocities in kilometers per hour. So let's take that and put it back into kilometers per hour. To do that, I'm going to multiply by 3.6. Actually, you're going to multiply by 3.6. What's the velocity in kilometers per hour for our moped? Which will round to 52.6 kilometers per hour. So it took a moped 6.5 seconds to go from 18 kilometers per hour to 53, effectively, kilometers per hour. And that's the procedure. Let's do a couple more, because language here is important. So let's take a look at the next one. Those of you who are looking at the clock, I know what time it is. I know I've only got about 10 minutes left. You are not going to have homework from me today. I am away tomorrow for the funeral of my grandfather, and you guys are going to have tomorrow's block to work through this. So I know I'm pushing up against the clock. Don't worry about it. It's not going to affect you negatively. You'll have tomorrow's class to work on this stuff. So here we go. What is the displacement of a train as it is accelerated uniformly from 12 meters per second to 40 meters per second over or in a 25-second interval? So again, same procedure. Write down what you know. What do we know? Someone tell me something we know. We know the time. The time is 25 seconds. Cool. What else do you know? So which one of those is the initial and which one's the final? VI is 12 meters per second. VF is 40 meters per second. Cool. What's the question asking you to find? Nope. The displacement. The first 4 words. What is the displacement? D is your unknown. So then again, let's look at those top equations. Which one of those equations would give you the displacement using only VI, VF, and T? We don't have an acceleration, so we don't want to use any of the equations that have an A in them. We're just told that the acceleration is uniform. Whatever it is, that acceleration is constant. The last one, we're going to use D equals VI plus VF over 2 times time. That's the only equation we can use based on the information that we're given. And so now let's fill it in. VI is 12, VF is 40. We're going to add those together, we're going to divide it by 2, and we're going to multiply it by 25. So you got to be careful how you plug this thing into a calculator. Plug it in, what do you get? Actually, I'm not going to go below, or not going to go to the right, I'm going to go below, because I'm going to use that space on the right to find something else. What is the displacement of the train while it is increasing its velocity? What number did you get, Emma? This is why I want all of you to punch into your calculator. It is not 51. Nope. You want to make sure, whatever you're punching into your calculator, use brackets properly. You want to make sure your calculator adds the numerator together before you divide by 2. Nope. It's bigger. Oh, and then you multiply by 25. You want 650. All of you make sure you can get your calculator to give you 650. And then what are the units on that, Riri? Almost. It's a displacement. So it's just going to be meters. So over 650 meters, all of you should be able to get your calculator to give you that. The one thing that might help you is if I included a set of brackets right here. If you put 12 plus 40 in brackets and then divide that by 2 and then multiply by 250, you should all be, sorry, 25. You should all get 650. Let's add a part B to this question. If you cannot get 650, let me know and I'll come work with you on your calculator. Let's add a part B to this question. What is A? What is the acceleration of the train if it took 650 meters, 6.5 football fields, to accelerate from 12 to 40 meters per second? So now I want to know what A is. When you're given a part B, if it is possible, use information that you're given and not information that you have calculated. In this case, it wouldn't really matter because 650 isn't rounded, but for the sake of my argument, let's just go use these first 3 to find A. If I want to use T, VI, and VF to find A, which equation am I going to use? I want to use T, VI, and VF to give me A. Let's go back to the first one again. The second one has D, I don't want to use D. The third one doesn't have time, and I want to use time. The last one doesn't have A in it, so what I want you to find, it's not there. So we have to use this first equation. So VF equals VI plus AT. We're looking for A, so plug in these 3 things to give us A. VF is 40, VI is 12, plus A times 25. What's the acceleration? I want you guys to solve that. The first step is to subtract the 12, and then you're going to divide by 25. Minus 12, minus 12. (40 minus 12 is 28. Then we're going to divide by 25. 1.12 meters per second squared. That is the acceleration of the train while it moves from 12 to 40 over 650 meters. Cool. Well, let's do one more. I think I have 4 minutes. So at this point, I think I've basically demonstrated all the skills. What the next 3 examples are going to do is it's just going to be really picky about how it communicates things to you. The language the questions use is going to all have some sort of deeper meaning. So we're going to let's take a look at example, this one, the third one. A car starts from rest, accelerates at 6.1 meters per second squared for 7 seconds. How far does the car move? What do you know based on what the question just told you? Based on what I just read. Write down everything you know. We know the time. The time is 7 seconds. What else do you know? So that's this piece. What else do you know? We know the acceleration. It accelerates at 6.1 meters per second squared. This is where the language gets picky. Emma just said the initial. What's the initial? The initial speed is what? So, Yuli, how do you know? Starting from rest. Starting from rest is a fun way to say VI equals 0. If you're resting, you're not moving. Starting from rest, starting from no motion means your initial velocity is 0. The question says, so that's the next piece. What are we looking for? How far does the car move? So what are we looking for? Yuli, we're looking for displacement. How far does the car move means what is the displacement? So then, in the minute we have left, what is the equation that we're going to use to complete this? Which one uses VI, A, and T to give you D? The second one. D equals VIT plus 1/2 AT squared. So D is equal to, VI is 0, which means what's going to happen in this equation? A very wonderful thing is going to happen in that equation. Don't pack up yet. What's going to be 0? This guy's going to be 0. So if when you multiply 0 by anything, it's 0. When VI is 0, this whole term disappears. And so you're going to get D is going to equal 0 plus 1/2 AT squared. So D is going to equal 1/2 times 6.1 times 7 squared. Now you may pack up. I'll have a video ready to go. My TOC will play a video for take you through the rest of this example and the next two, and then you'll have all of tomorrow's block to work on what I will assign to you. Have a great day. Enjoy my digital self tomorrow. I'll be back on Wednesday to take up any questions you may have about this stuff. There we go.